So the last problem that I want to look at for an example of this procedure is a slightly more applied problem. And this is the following. Let's say we have some sort of cost function, and we also have a production constraint. So let's say we're producing a certain, let's say we're producing two things. We'll call them devices just to be, very specific. X is the amount of device 1, and Y is the amount of device 2. And specifically, we have a production constraint, so it's subject to it says that the maximum total amount, or combined total of these items, these devices, is equal to some value. We'll just say 60 for argument's sake. That means that X plus Y is equal to 60. Well, we can go through and directly apply our Lagrange method. We'll also suppose, for argument purposes, that C of xy is the cost function. For producing X and Y. Now, this can take a lot of different forms in general, but for arguments purposes, we'll just go through and say it's some sort of quadratic function of X and Y. Say for certain reasons, it's going to be 5x squared plus x times y plus 2y squared plus 500. So for any amount of the quantities x and y, this function is giving us the exact cost of production. Maybe it costs a little bit more to produce a certain x amount of x versus a certain amount of y. So this coefficient of x squared is bigger than this 2 right here. But you can think of this cost function as being the exact function, mathematical function, that gives us the exact amount that it costs to produce a certain amount of units x and y. So we have that this is directly Lagrange multiplier, or I should say it's a constrained optimization problem that is directly in the form for application of Lagrange multiplier method. And that's because directly we can construct our Lagrange function, which is going to be capital F of xy and lambda, which is 5x squared plus xy plus 2y squared. It's the function that we're optimizing. And that'll be minus lambda times the constraint function, which is x plus y minus 60. Because our function lowercase f of xy that we're optimizing is this cost function. We want to find the optimal cost. Right? When we have this constraint right here. This is our constraint function, g of xy. So our Lagrange function will take this form right here, where this is our f of xy minus lambda times g of xy minus c. So going through and applying our procedure, we have our three equations that have to be true at any critical point of f. The first is that the partial derivative of f with respect to x has to be equal to 0. When we take the partial derivative of this with respect to x, we get the equation 10x plus y minus lambda is equal to 0. Or y is equal to lambda minus 10x. Equation 2 is that the y partial derivative of our Lagrange function has to be equal to 0. This is going to tell us that x plus 4y minus lambda has to be equal to 0, which is the same thing as the equation x is equal to lambda minus 4y. And then lastly, equation 3 says that the lambda partial derivative of our Lagrange function has to be equal to 0, or negative x plus y minus 60 has to be equal to 0, which is just saying that the constraint has to be satisfied. So we have three equations for three variables, and it turns out this is actually a nice system because it's a linear system of equations. So it's a little bit easier to solve than the previous example problem. But I wanted to go through both to show you that it's possible to do even in more complicated scenarios. The first step is to combine equation 1 and equation 3. We'll use our elimination procedure from before. In general, there's multiple different ways of going through and solving a system of equations. But typically, I think that elimination, is the most straightforward method of doing it without any linear algebra background. Now, with linear algebra, you can deal with very large systems of linear equations, but the idea here is that we'll kind of just stick to one of the most straightforward methods here, which is elimination. So I'll take equation 1 and equation 3. If I plug equation 1 into equation 3, I get the equation x plus lambda minus 10x is equal to 60, which is the same thing as the equation negative 9x plus lambda is equal to 60, or x, if we solve this equation for x, is equal to lambda minus 60 over 9. This is, we've eliminated y, so we'll call this our equation 1 star. In a similar manner, we can go through and combine equation 2 and equation 3. And this is going to give us the equation. When we plug in for y into this equation from equation 2, or we plug in for x, we plug equation 2 into equation 3, we'll get lambda minus 4y plus y is equal to 60, which is the same thing as lambda minus 3y is equal to 60, which we can solve for y to get that y is equal to lambda minus 60 over 3. And so we have, from equation 1 and equation 3, the relationship between lambda, the Lagrange multiplier, and x. When we do equation 2 and equation 3, we get an isolated equation relating y and lambda. The last step here is to go through and combine these. So we combine this equation 1 star with this equation 2 star, just like we did in the previous problem. So from equation 3, is that x plus y equals 60. So x is lambda minus 60 over 9 plus lambda minus 60 over 3 is equal to 60. So this gives us an equation that we can actually isolate for lambda, and we can directly solve for lambda here. So if we go through and do this, I think that the easiest thing to do is probably multiply both sides by 9. That will give us the equation lambda minus 60 plus 3 lambda minus 3 times 60 so 3 times 60 then is equal to 9 times 60, or the equation 4 lambda minus 4 times 60 is equal to 9 times 60. Which is the same thing as the equation 4 times lambda minus 60 is equal to 9 times 60. Which is the same thing as lambda minus 60 is equal to 9 times 60 over 4, which is 9 times 15, or 135. So lambda is equal to 60 plus 135, or 195. So our Lagrange multiplier for this problem is 195. And then the last step of the problem, I'll add one more page here so we can go through the last step of the problem, which is take this and directly plug in for x and for y. So we have that x is equal to lambda minus 60 over 9. This is going to be 195 minus 60 over 9, which is equal to 15. So x is our solution x equals 15 is our number of x units we should produce. And y is equal to lambda minus 60 over 3, which is 195 minus 60 over 3, or 45. So what that tells you is that the minimum value, and you can go through and actually classify this as well using the the classification test for the Lagrange function, but that involves classification tests for a function of 3 variables. So I'm going to avoid that for right now. The main idea here is that turns out that this is a minimum value, so the minimum cost c of xy, minimum cost of c of xy, subject to the production constraint x plus y equals 60 is x equals 15, y equals 45. So if we produce 15 units of x and 45 units of y, we minimize the cost while maintaining our production constraint of 60 units. And here we see a plot of the cost function. It's a contour plot with a gradient field. The constraint is this white line right here. This is a constraint x plus y is equal to 60. And in green here, you see the gradient of the constraint. It's this vector right here. And then in orange, it's the gradient vector of the point at the solution point, which we found to be 15, 45. Right? And very clearly, this solution point is the only point at which the gradient vector will be perpendicular to the gradient of the function, will be perpendicular to the gradient of the constraint. And very clearly, right, this is exactly what the Lagrange multiplier method is predicting. And not only that, but the constant of proportionality, in this case, is 195. This is exactly the Lagrange multiplier. Right, so for any other point on this constraint curve, the gradient of the function is not going to be parallel to the gradient of the function itself. This is the only point that satisfies that, and thus it's the only solution to our constrained optimization problem. So this is very, very, very neat. So this is a very, very powerful procedure. It applies really any time you have some sort of cost you want to minimize, or any time you have a function that you want to minimize or maximize, but you also have a constraint that you have to take care of. Furthermore, you consider a more advanced question, a more complicated question. You could say, what happens if the constraint is different? Let's say we increase the constraint by a little bit, or decrease the constraint by a little bit. How is this going to affect the final outcome here? So I'll call this part B. If the first part of this problem, we'll say, is just part A, you have some fixed constraint. Part B is, say, a more general problem. You could say, suppose x plus y equals t, where t is a new production quota. What's going to change here? In part A, t was equal to 60. But what happens if t is a different value than 60, if we sort of increase it a little bit or decrease it a little bit? And what happens is the following. We still have our Lagrange function, but the Lagrange function becomes a function of t and still of all the other variables as well. So x, y, and lambda. And what also is a function is actually x, y, and lambda are functions of t. Right? Assuming we have that value of t, we can go through and do the Lagrange multiplier method, just like we did before with our Lagrange function. But the idea is that the Lagrange function, right, is now going to depend directly on, just like it did before, x, on y, and on lambda, but it also depends on t, because the Lagrange function is going to be the cost function minus our constraint function, which is our lambda times our constraint function, minus this new value, this new production quota. So say for a fixed value of t, you can actually go through, just like we did before, for any value of t, we can go through and directly solve go through the same procedure as in A, which means we go through and we solve df dx equals 0, df dy equals 0, and df d lambda equals 0, and solve for x, y, and lambda, just like we did before, but these are going to depend on that new production constraint, t. Or another way of saying that is that there are functions of t. So let's say we do that. We go through and we get x of t, y of t, and lambda of t, such that the x partial derivative at this r of t equals 0, the y partial derivative r of t is equal to 0, and the z partial derivative is equal to 0. And not only that, we'll call the minimum value, which is the minimum cost, m of t, because that's also going to depend on this new production quota, m of t. Specifically, it'll be the cost function at x of t and y of t, which we know is the same thing as the Lagrange function at x of t, y of t, lambda of t, comma t. Because the Lagrange function satisfies that equation 3, which is that the constraint term holds, or g of xy minus t is 0. So we could say, what's the rate of change, or the derivative of this minimum cost, this m of t? And the correct answer to this question lies in the multivariable chain rule, because this minimum cost depends on a number of different things. It depends on t independently. It also depends on x, on y, and on lambda as well. These optimal solutions for x, y, and lambda, which all also depend on t. So from the multivariable chain rule, the rate of change of the minimum cost, m prime, or dm dt, is going to be the partial derivative of f with respect to t plus the partial derivative of f with respect to x times the partial derivative, or the single variable derivative, of x with respect to t plus the partial derivative of f with respect to y times dy dt plus the partial derivative of f with respect to z times dz dt. Or not z, but lambda, sorry. And you might think, oh wow, this is getting long and complicated. Like, how are we going to figure out all of these things? Could we possibly have enough information to figure out all of these things? And the answer to that question is relatively simple. These partial derivatives, df dx, df dy, and df d lambda, are all zero, because x of t, y of t, and lambda of t all satisfy the condition of the minimum, the fact that it's minimizing this Lagrange function, or it's minimizing the cost subject to our constraint. And because of that, the conditions of the minimizing x of t, y of t, and lambda of t, minimizing and being critical points of our Lagrange function, are exactly that partial derivatives are zero. So this is zero. This is zero. And this is zero. It's guaranteed to be zero by the sole fact that we ended up going through and solving this system of equations for this specific value of t. Now, you could go through and do that, but in general, it'd be a little bit complicated. You have to keep track of everything and solving for that. So it's much easier to do it this way, because it kind of completely removes our goal, or not our goal. It removes our the long and complicated and arduous process of going through and solving that system of equations in general for a general production constraint t. And what happens here is that we have the following result: that m prime of t is directly equal to the partial derivative of f with respect to t, which, if we go up and we look at f, the partial derivative of capital F with respect to t is going to be negative lambda times negative 1, or lambda of t times negative 1, which is just equal to lambda of t. So what this is saying is that the rate of change of that minimum, of the minimum cost, is directly equal to the Lagrange multiplier at t, at a given production constraint t, where that dm dt is equal to lambda. This is true for any any Lagrange minimization problem, which is quite amazing that we can do this and get this general relationship. It's very, very, very powerful. What it's saying is that we can use this, right? We know that if, let's say, for instance, we have a small change. So we have a small delta t, or a small change in production quota. Call this delta t. Well, we know from linearization that m of t at a given point close to delta t. The delta t here is t minus t naught, where like t naught, say, is like our initial production quota and t is the new production quota. If delta t is much less than 1, so it's very small, I should say it's small relative to the function, so we'll just say small, then m of t is going to be approximately equal to the minimum value at t naught plus the derivative m prime at t naught times delta t. This is our linearization approximation for a single variable function. And what we've just shown is that this is the same thing as m of t naught plus lambda of t naught times delta t. Or for small delta t, that m of t minus m of t naught, the difference in the minimum at a given production quota t naught in t for small differences is approximately equal to lambda times t naught, or lambda of t naught, the Lagrange multiplier at t naught, times this difference, delta t. So this is a very, very useful thing and useful rule of thumb that can be used to help us figure out, say, how this minimum is going to change without doing much calculation. So for instance, let's say we take our previous problem and we change to a new production quota. Right? In the first problem, or part A of the problem, our production quota was the production quota of 60. We had a production quota of 60, so that's our T naught for part A. So T naught is the production quota from the first part. Let's say we can increase that a little bit. We can go to, say, T naught is equal to 61, say. Or so T, say, our new production quota, we can raise it up to 61 maybe. Right, then the minimum, to use this equation, the minimum at 60, or the minimum at 61, minus the minimum at 60, the difference in minimums between these two problems is going to be approximately equal to our Lagrange multiplier from the first part, which is the Lagrange multiplier corresponding to a production quota of 60, which is 195, multiplied by 61 minus 60, or 1. Right, and so approximately speaking, the minimum is gonna increase, but the difference in the minimum at the production quota of 60 and the minimum at a production quota of 61 is going to be 195, approximately. It's not an exact equation because whenever you're doing a derivative approximation, you always have some error. But the idea is that we can directly use this and do this process. And we can do it very quickly. Right? We don't have to go through and actually solve the new problem for that new production quota, which is very, very useful. But that'll do it for the lecture today. Thank you very much for tuning in, and I hope you learned something. Have a great day.